The Continuous Electron Beam Accelerator Facility is a new laboratory for basic nuclear physics research. At CBAF, scientists can advance our understanding of matter itself by probing the quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. CBAF has an educational mission as well. The CBAF Science Series features scientists and engineers who are gifted at making their work not only informative, but fun. The Science Series is held once a month during the school year in the CBAF Center Auditorium. The presentation is live, spontaneous, and for the most part, unrehearsed.
Good evening. Welcome to the CBAF Science Series. Before I introduce tonight's speaker, I want to remind you about next month's program, which is on Wednesday, December 13th, and it's at 7:30 p.m., so that our speaker can appear on the television before he appears here in our auditorium. The topic of that talk is lightning and severe storms, and Dr. Dwayne Harding from WTKR Channel 3 is going to be our speaker. It's particularly exciting for me to introduce tonight's speaker and tonight's topic because it is central to the experimental program at CBAF. Our speaker is Dr. Gail Dodge. She's an assistant professor at Old Dominion University. Dr. Dodge grew up outside of Boston in Massachusetts, and she has one younger brother who is a fighter pilot in the Air Force. She was always interested in math, and when she took physics as a senior, was fascinated with how calculus really came to life. Her high school physics teacher invited her to work at an accelerator laboratory near her town, and she got very involved and interested in experiments there. After completing high school, she went to Princeton as an undergraduate, unsure about whether she would major in political philosophy or in physics, and in her sophomore year, physics won out, showing her excellent judgment. After completing her bachelor's degree in physics at Princeton, she proceeded to California, a place she'd always wanted to live for a while, went to graduate school at Stanford, got a PhD in nuclear physics there, and then left for 3 years in Europe, where she got to do experiments and live in Amsterdam. In January 1995, she moved to Virginia, joining Old Dominion University as an assistant professor, and she is one of the physicists working on experiments at CBAF. Please join me in welcoming Dr. Dodge to talk about interpreting data from particle detectors.
Hello. As Dr. Hartline just said, I want to describe to you how we use particle detectors in order to learn more about physics. In other words, how do we get data from particle detectors, and how do we learn something? So the title of my talk is Interpreting Data from Particle Detectors. First of all, what I have to do is review very quickly what the structure of matter is, because I'll mention many times throughout the course of the night electrons and protons and neutrons and subatomic particles. So what I want to do first is just quickly remind you what are protons and neutrons, and I'm going to do that by showing you this picture. What you have here is some aluminum foil. I have some aluminum foil right here. It's very thin. But there are 250,000 different atoms in one sheet of aluminum foil. So an atom already is something that you have no hope of seeing with your eyes, of course. An atom is shown right here. It has a nucleus in the center, and then it's surrounded by electrons. Electrons are orbiting the nucleus. Now this nucleus, if you blow it up even more, looks like this. It's made up of protons and neutrons. And then if you look even inside one of these protons and neutrons, then what you see is 3 quarks. So quarks are what are inside of protons and neutrons. That's what we're trying to study here at CBAF, how the quarks interact with each other to form protons and neutrons, and how the protons and neutrons make up the nucleus. But the protons and neutrons are what's inside the nucleus of the atom, and we'll mention that. That will be relevant later in the talk. So what I want to do is to describe to you First of all, what are detectors? What are particle detectors? How do we learn something from them? first thing I have to do is to remind you that there are subatomic particles all around us in the form of cosmic rays. Subatomic particles, like protons and neutrons, are not just abstract particles which we can talk about, in the laboratory. They're really around us. Right now, at all times, there are cosmic rays coming down from the sky, and those are subatomic particles. And let me tell you a little bit about those cosmic rays. Okay, as physicists, we like to describe cosmic rays as the great accelerator in the sky, because they're raining down all these particles on us. And it's useful because we get high energy particles, and we can, for instance, look at our detectors and see how they react to those particles, and that helps us debug, for instance, the detectors. We call it the great accelerator in the sky for that reason. Now, what are these cosmic rays actually? What type of particle are we talking about? Well, 75% of the particles that reach us at sea level are muons. A muon is essentially a very, very heavy electron. You also have protons and electrons as part of that shower that's coming down all the time. Now, the interesting thing about cosmic rays is that we actually don't understand really the source of them. They're very, very high energy. For instance, these muons are on average about 2 GeV. That's about the energy of the CBAF electron beam. And they're coming from the sky. Here we have to build a big, huge building and spend years and years developing something which produces electrons of the same energy that are already coming down from the sky. So that's one interesting point. But what causes these very, very high energy particles? That's really not understood. Some particles have been measured, some cosmic rays have been measured, which are actually 200,000 times more than the energy of the beam at CBAF. So not only are the average ones about the same as the electron energy here, but many of them are much, much more energetic. And we don't know what in the universe can cause them, but we do know that they come down. What is the rate? How many cosmic rays are coming through me right now? Well, a good rule of thumb is that you have one cosmic ray per hand per second. So every second, a cosmic ray is basically coming through an area about the size of my hand. So definitely they're all about us. We're bathed in these particles. It's part of the background radiation. There's always some radiation around us, and it comes partly from these cosmic rays. And as I said, because they're all around, because you can always find them, we use them very often to help get the problems out of our detectors. So what I want to show you next is a demonstration of cosmic rays that are coming in right at this moment into a detector in another building at CBAF.
Yep.
So, excuse me?
We have to hold on that a little bit.
Oh, okay. I'll show you a picture of the detector that you're going to see. It looks like this. It has 3 different layers of scintillators, basically. So what happens is a cosmic ray comes through here, and it produces a signal here, produces a signal here, and it produces a signal in this layer. And so what happens is you can look for, it basically looks like a triangle. You see a signal on each side of the triangle, and then you know that a cosmic ray came through. So this detector is right now sitting 2 buildings away over in another part of CBAF, and cosmic rays are coming through it right now, even as we speak. And I'm going to show you if we're ready.
Give me some time.
Oh, okay.
Later on.
Okay, we'll actually come back to this, but I want to show you what the particles actually look like in this detector a little bit later. Okay. So, do we see detectors in everyday life? I mean, are detectors some kind of an abstract concept which doesn't have anything to do with our life? I mean, do we have detectors all around us? Can you name any detectors that you use on a regular basis? Smoke detector, exactly. Yeah, that's a good one. That's an important one, right? It saves your life. So, any other kind of detectors that you know about? Radon detector, yeah. That's a good one. In fact, there are detectors everywhere. A detector is basically something which allows us to detect the presence of something. Now, one very obvious detector, for instance, is your eye. Your eye is a detector, it sees light. If there's a house over there, it's not that I'm touching the house. I see the house because light is scattering off of that house and into my eye, and it's forming an image. and that image is transferred to my brain. So your eye is a very important detector. Also, your finger is an important detector, right? What happens when you touch something? What do you actually, what's actually going on there? It's very different from seeing that thing, right? You touch something, and you have some firing of your neurons, your nerve endings feel that pressure, and then you have an electrical signal that's traveling all the way up your arm and into your brain. It's really an electrical signal going through those nerves. So your finger is very much like the kind of detector we use on a regular basis. Okay, other very common detectors are microscopes, we're all familiar with, X-ray detectors, for instance, at the airport, or there's, if you break your leg, you get an X-ray, right? They want to see if it's broken. Metal detectors, there's also medical imaging. That's a very, very big field right now, where you can take, for instance, a CAT scan of someone's brain to see if there's a tumor, or you can do MRI, magnetic resonance imaging, or positron emission tomography, for instance. All of these are using particles and using particle detectors to take an image of your body to try to diagnose whatever problem you may have. And I think it's important for you to know that here at CBAF, not only are we doing nuclear physics, but there's a whole detector group which helps build the detectors that we use. But at the same time, they are also helping to develop new kinds of medical imaging detectors for use, later on down the road. So detectors are basically everywhere, in all facets of life. So a detector is not a scary thing or a strange thing. The question is really, now how do they work? We use particle detectors to see subatomic particles, which we can't really see with our eyes, because we want to learn about the physics of how these particles interact, so we need a way of knowing if those particles are present. We need to know what kind of particle we have or what the energy is like. So let me try to explain to you how we use these detectors in order to know that the subatomic particle is there. Okay, what happens? Basically, a subatomic particle, let's say a proton. A proton is traveling fast through the air. That proton is in some ways like a bullet, right? What happens when a bullet comes onto a body or a piece of material? How does that bullet stop? What actually is going on with that bullet? That's because it's very similar to what's happening to a high energy proton when it comes to a detector. It's expending energy. That bullet is coming into the material and it's slowing down, right? And eventually it stops. And so the bullet is losing energy, and it's giving energy to the material that it's stopping in, right? It's heating up that material, for instance. So it's the same way with a proton, or any kind of high energy particle. Basically, the detector is just a piece of material, for instance. That material sees the particle by slowing it down. So that particle's energy is actually transferred to the material. So just like the bullet transfers its energy to a material when it's stopping, and it then causes heat or whatever, the same way a proton is slowed down in a material, and then that material gets the energy. Now, what does the material do with that energy? How do we see that energy in the material in a way that allows us to detect it? Well, what happens is that energy deposited in the detector material turns into light, or it turns into electrons. So we choose materials which are very good at turning energy into light or energy into electrons, because what can we gather? We can gather up the electrons as an electrical pulse. If you have a whole bunch of electrons produced in a material that are traveling along, you can actually put a wire on that and you can get that signal off of the detector. So the electrons give you an electrical pulse. The same way, light can actually be seen with your eye, for instance, or you can photograph that light, or there are ways of turning light into electrons also. So then the point is that you can get an electrical signal that came from that light. So the bottom line is that the energy is deposited in the detector, and that energy is expressed or turned into light and electrons, and we gather up that light and those electrons. And that's essentially what's going on when we see a particle in a detector. Okay. Now, I want to show you how this works, where the particle is slowing down in the detector and you actually see an electrical signal out. And to show you that, we're going to do a simple experiment up here. And this is basically what's going on in the experiment. So I want to explain it to you first, and then when you see it demonstrated, you'll have a better idea what's going on. Okay, what we have is a radioactive source. In our case, it's bismuth-207, and it produces electrons. It also produces gamma rays. The electrons are about 1 MeV, which, if you know what that unit of energy is like. So the electrons can travel through the air, and the gamma rays can travel through the air. By the way, what's a gamma ray? I'm using some words, and maybe I haven't explained them. What's a gamma ray? Does anyone know? A gamma ray is just a photon. It's light. Light is a photon of a certain energy. But you can have a large spectrum of possible energies for a photon. And gamma rays are very high energy photons. And some radioactive sources, like the one we have up here, just naturally emit gamma rays. Also, this radioactive source, as I said, emits electrons. It just spontaneously ejects gamma rays and electrons from the nucleus of the atom, and it turns into another nucleus. That's what's happening inside the radioactive source. So anyway, we have the source up here. It's producing electrons and gamma rays. They're going through the air, and they're going to hit this detector. The detector is in green. Okay? And the detector, as I said, slows down those particles and turns that energy into electrons. And actually, in this case, it turns that energy into photons. The photons are produced, and here in this photomultiplier tube, the photons are gathered up, and they're turned into an electrical pulse. So here we have the detector, where the particle is depositing its energy, where it's slowing down and stopping, in some cases. Electrical pulse is produced here. And then it comes to an oscilloscope. An oscilloscope is essentially just a way of seeing how big of an electrical pulse we get. Has anyone worked with oscilloscopes before as part of for instance, your labs at high school? Okay. An oscilloscope is something which, as you see here, it displays the voltage of the electrical pulse that you get as a function of time. And when you get an electrical pulse from this photomultiplier tube, what you see is a pulse like this. So first there's nothing there, then you see the pulse, and then it decays away back to nothing. And the interesting thing about this is that the amplitude of this pulse, the height of this pulse, the distance, the largest part of the pulse compared to zero, that amplitude actually measures the energy that was deposited in the detector. Because for all the energy that was deposited here, you produced electrons that came along, and then the more electrons you have, the more energy that was deposited, the more electrons you have. The more electrons you have, the bigger your electrical pulse, and the bigger your signal. And that's really the key to particle detectors and how we know that there was a particle depositing energy there. So what you're going to see in this demonstration is that we're going to show you this signal on the scope, and then we're going to put some things in the way between the radioactive source and the detector. And what happens is, when a particle goes through these absorbers, I'm calling them because they're absorbing some energy, then some of the energy from those electrons is deposited here instead. It's deposited here in the way. So this energy doesn't all reach the detector, so the signal that we see from the detector should be smaller. So that means that this amplitude should be smaller. So let's see if we can successfully show this to you. I want to switch now to the oscilloscope. Where's Steve? Okay. So what you see, first of all, let's make sure that that's the computer. We'll come back to that in a second. Okay. The oscilloscope is right up here, actually. We're shielding it from your view because we don't want the light messes it up. But what you have is right here is the radioactive source, and then there's a small gap of air, and then here is a detector. And so right now there's nothing between that radioactive source and the detector, and this is the signal you see. So you're seeing the result of many, many particles being emitted from that radioactive source and seen by the detector. Each one of these traces, as we call it, each one of these pulses represents one particle that was seen. And the amplitude, as I said, the height of this pulse corresponds to the energy that was deposited in that detector. So what do we see? As I said, there's two kinds of particles involved here. There's electrons and there's gamma rays. The gamma rays show up as the many, many different energies, low energy stuff here. So very low amplitude, which corresponds to low energy deposited in the detector. The electrons, on the other hand, are these bigger signals here. This means every time you see this, it means that there was an electron that came into the detector. Now, the electrons can actually produce a couple of different energies. It's not always exactly the same energy is deposited in that material. Some electrons go right through the detector and don't deposit that much energy. That does happen sometime. But usually, a lot of the energy from the electron is deposited in the detector, and we see a very big pulse like this. So what do you think is going to happen when we put in a piece of plastic in between the radioactive source and the detector? What should happen to this picture? Okay, let's see what happens. He's putting it in. Do you see a difference? Let's take it out and put it in a few times. There's out, and now it's in. Now it's out. Now when it's in, let's keep it in for a minute. When it's in, you see the maximum pulse height we see is here. Occasionally you see a really big pulse that's coming like this. That's probably a cosmic ray or something. You can never get rid of those no matter what you do with this piece of plastic. So you're always going to see the occasional big pulses here. But the interesting thing is that the maximum pulse height here is quite a bit smaller than when the plastic is not there. Let's take the plastic out again. See, it went all the way down to here. What I'm trying to show you is that some of the energy from the electrons are being absorbed by the plastic, so less energy can go into the detector. So we see a smaller signal here. So if we had a way of recording the height of every single signal we see, then we'd have a way of finding out the energy of every single particle that came into the detector. And that's basically what we do, ultimately. Let's try, now here again you see that you have one, this is where the most of the electrons are. Let's try putting in two pieces of plastic, so double. Now it goes way up to here. So we're getting rid of some of the electrons. Some of the electrons are no longer reaching the detector because they're stopping in that plastic. You could say that the plastic is a detector, except that the plastic is not very good for producing electrical signals, so we can't use plastic very well. So we don't actually like to use plastic as a detector. Instead, we use the scintillator. There, it gets smaller. So we use a scintillator as a detector because we can turn that signal efficiently into an electrical pulse. So this is okay, now for the lead brick demonstration. As I said, we have gamma rays here. All these low amplitude things are gamma rays. Now you may be asking yourself, how come the gamma rays are still there every time we put in a piece of plastic? These low energy things keep staying there. Now he's put in the lead brick, and you see almost nothing. So now we've stopped everything. All the electrons and all the gamma rays that were coming from that source have deposited all of their energy in the lead brick, leaving no energy to get to the detector. Now, occasionally we see a pulse here. Why is that? Cosmic rays. You can never get rid of them. It's great because you can use them, but you can never get rid of it. So this is essentially what we do with this at a small scale is exactly what we're doing with all the detectors we build at CBEF. We're building and we're putting together pieces of material that will slow down particles and produce big electrical pulses that we can then record. And I'll say a little bit more about that in a minute. Okay, are we ready to see some more cosmic rays? Let's switch over to the computer screen. This is Cole Smith, who is at University of Virginia. And he's working on a big detector here as part of Hall B, the CBEF, the class detector. It's a calorimeter. Can we switch over to the... Okay, this is the picture I showed you before, which has the different layers of scintillators. These strips are scintillators exactly like the one that's down here. This piece of material right here is a scintillator. It's just the same as what you see right here. So it's going to see protons. Yeah, let me show you an example. We'll actually come back to that in a moment. Okay, so these are the strips of scintillators that you have. And you have different layers of them, and a cosmic ray is going to come through all of them, and we'll see, every time it hits a scintillator, we see the picture. So here, on this side of the triangle, this strip saw a particle. Here, this strip saw a particle. Here, this strip saw a particle. And if you look at the intersection between the places where the particles were seen, then you see where the cosmic ray came through. Now what you're seeing is a detector. As I said, it's 2 buildings over. It's actually taking data right this minute, and the data is being transmitted here through the World Wide Web or through the Ethernet, so that you can see it here in real time. Here's the data up here. These are cosmic rays that are coming in and being detected at this moment. Now there's some interesting things about this detector that you may want to know. First of all, a lot of people are working on this detector. It's a big effort. It's a huge detector. It's like probably half the size of this room. It weighs something like 16 tons. And this is one very small part of a much bigger detector where we put different layers together. And I'm going to show you a picture of that in a little while. But this is one small part of an overall large detector we're building for one of the halls here. But it's not so small, you know. It's 16 tons. That's the equivalent of about 3 school buses filled with kids. So it's a pretty big thing. We couldn't bring it over here to show it to you. But we leave it in the other building, and we transmit the data through the computer, through the Ethernet, so you can see it coming in even as we speak. So what do these different colors mean? Well, basically, the higher up you go is the more energy that was deposited. So you see that a lot of energy is deposited in this place because there was some deposited this way, some deposited in this scintillator, and some deposited in this scintillator. The total gives you a lot of energy. Actually, quite a bit more cosmic rays are coming down than the ones that you're seeing every 1 second or so. And that's because we're weeding out the sort of undesirable events, the events that show stuff all over the place. Because sometimes you have a nice high energy muon that comes down, and that's what you see. A very high energy particle which comes cleanly, goes all the way through. And in fact, these high energy muons from the sky are not even stopped in this huge detector. These detectors were designed so that they could stop all the particles produced when we have the beam going at CBAF. So that's pretty high energy stuff. But these cosmic rays are coming right through the whole thing. They can go way down into the Earth before they stop sometimes. So this is what's going on right now. And this is all part of the testing process we go through to understand a detector. You know, you build a detector like this, and then you have to try to make sure it's working. You have to try to understand what's going on. And so we use these cosmic rays to say, okay, everything's working. We see signals in all of the little pieces. And it takes quite a while to get through, to learn everything you need to learn, which you can learn with the cosmic rays. Okay, I think we should turn that over. Oh yeah, let me as I said, we have pieces of scintillator in this detector. Those scintillators produce light. So this is one of those detectors which actually produces light instead of electrons. The light comes into these photomultiplier tubes. I'm sorry, here's where the scintillators are. The light travels along the scintillator into an optical fiber, which brings it up and into a photomultiplier tube. And it's this photomultiplier tube which turns the light into electrons. Remember I said that sometimes we get photons, sometimes we get gamma rays, and we turn them into electrons, into electrical pulses so that we can see them later, so they can travel through long cables and we can see them later with our computers. So we have the light produced here in the detector. It's traveling through these optical fibers up to a phototube, which turns it into electrons. And here's an example of one of these optical fibers. What you see right here is this thing right here. All these fibers lead you from the detector up to the photomultiplier tube. And let me show you what happens. Here I have sort of a red laser kind of thing. And let's say I get a photon here. The photon is seen up here. So here's the thing which turns the light into electrons, and here's the light coming in down here from the detector. So if I go across like this, each of these fibers channels the light up into the appropriate little place up here. Can you see this okay? The light is traveling along, it's coming into the fibers here, and it's coming out up there. So you can take light from all the different layers of detectors and feed them nicely up into one little place here where you can gather them, where you can turn them into electrons. So you should see a pattern moving along here as I scan across these optical fibers. If you're having trouble seeing it from where you're sitting, feel free to come down afterwards and look at it more closely. You can probably see it a little bit better if you come up close and check it out later. Okay, so this is the detector from Hall B, which is operating right now. Let's turn that off. Excuse me? Okay. I think it is a good time to show you an example of a scintillator. As I said, the detector in this case, the thing that was producing the photons, was a scintillator. Here I have an example of a bunch of different scintillators that you can see. There's a UV light shining from over here. The UV light is shining along here and into this black area here. So the UV light you could think of as like the cosmic ray. It's depositing energy in the scintillator, and then the scintillator produces light. So let me show you, for instance. Maybe we should turn the lights down a little bit for this as well. Here, this is optical fiber, just like the one I showed you before. It carries light from one end to the other end. I put one end in the UV light. Can you see? Can you see the green light at the end of this fiber? See that? The interesting thing about scintillators is they come in all different sizes and shapes. For instance, here's a block, and when I put it in UV light, it turns out to be blue. Whereas these fibers turn out to be green. And you can get all different colors. You have red ones, you have green ones, purple and blue. And this scintillator, for instance, this is exactly like the piece of scintillator that was in that display you saw. The cosmic rays were coming into a scintillator like this. They were producing photons out the end, just like the UV light is being channeled out the end here. You see this? And these photons here were being fed into here and then up to a photomultiplier tube. So again, this is up here. You can come and look at it more closely afterwards if you like. The scintillator? Yeah, it's not even glass. It's plastic, actually. And it is very special. We chose it just for the fact that it produces light so nicely. So you can't just put any piece of plastic in a UV light and get light out this way. You have to choose your material wisely. The other thing we have here is a bunch of little remnants and pieces of optical fibers that were used to build these things over here. I mean, there's millions of these things being built, and every time, sometimes there's a little piece that falls off the end. We have a lot of those pieces here. If you're interested, you can take one at the end and try and shine some light at it and see it come out the other end. So we have some pieces. But what I want you to be very careful of is you don't hurt yourself with these things. They're not very sharp, but obviously you shouldn't poke your eye out with these things, you know? Okay. So I've shown you a whole bunch of different kinds of detectors, scintillators especially. Now I want to tell you what we do with those signals. You know, I mentioned several times that we keep trying to turn the photons into electrons. We gather up these electrons as electrical signals. So what do we do with those electrical signals? How do we actually get physics information? It's one thing to see a light, you know, it's another thing to see a signal on the scope. It's another thing to actually learn what was the energy of that particle, what direction was it going. Well, what we do is the electrical signals that come out the end of the wire, they're sent through very long cables to a set of data acquisition electronics. So we have in one place the experiment going on with a detector sitting there, and then we have long cables that come away from that detector that go over to where we sit, where the people sit, to look at all this stuff. And we see we have electronics there. And what those electronics do is that they digitize that amplitude of that pulse. So every time you have something hitting the detector, you have an amplitude. That amplitude is proportional to the energy that was deposited in the detector, and we digitize that amplitude so that we can look at it later. We also look at the time of arrival of these pulses. Now, why would we do that? Well, it turns out that if you want to see whether this neutron that came out over here and this proton that came out over here are actually coming from the same nucleus, then you have to look and make sure that they're correlated in time. So it turns out to be very, very useful for us to see what time the pulse came to a detector, as well as how much energy was deposited. So we digitize those two variables, the amplitude and the time of arrival, and then we record all that digitized data with computer. Of course, we save the data, we don't just throw it away. And then what happens is, while an experiment is going on in a hall over there, we're sitting over here, we're looking at that data as it comes in. We try to make sure we understand the data as it comes in. We try to make sure all the pieces of the detector are working. But we also record the data so we can replay it later. Now, what typically happens in the kind of experiments that I work on is that you can spend 2 years looking at that data again and again to try to make sure you really understand what's going on. For instance, I said that the amplitude of that pulse was proportional to the energy that was deposited, but you have to know what is that proportionality constant. You have to know how much amplitude corresponds to what energy. And these are some of the things that we have to figure out later by replaying the data again and again. So this is how we process those signals. And then, as I said, we have to analyze the data. Now, what kind of things do we have to figure out there? Well, ultimately, what do you want to know from a detector? You have a detector, you spent 3 years building it. What actually information do you need to get out of that detector? You don't want just a flash on your screen every time there was a particle that came through. You want to know more specific information. You need to look at that data and find out, first of all, what type of particle came into that detector. Was it an electron, a proton, a neutron, a muon, a cosmic ray, whatever? You need to tell the difference between those different types of particles. And one way you do that is by looking at the energy, again, that was deposited in that detector. For instance, a cosmic ray, we saw, they give you very big signals. Cosmic rays produce a lot of energy in a detector, whereas an electron is very, very light. I mean, if you compare different kinds of bullets, you know, of course I don't know different kinds of bullets, but let's say you had a very heavy bullet and a very small bullet. Obviously the very heavy bullet is going to slow down more. And the very light bullet may go right through, you know, some thin piece of material. And so by looking at the energy that actually came into the detector, you can tell the difference between these different particles. You also want to know what that particle's energy was, of course, as we mentioned, and also what direction that particle was going. Because very often it turns out that the direction that these protons are coming is as important as their energy. You very often want to know how many come out at 30 degrees, how many come at 60 degrees, how many come at 90 degrees, and that helps you learn also some details of what was going on inside the nucleus that led to you producing these particles. So you have to analyze the data to find out these three quantities. And then comes the hard part, even more hard than the things that came before, and that's the interpretation. So you know the type of particle, you know, so you know the energy of the particle, and you know what time it came and what angle it came out at. How do you actually learn something about the physics in that case? Well, one thing you can do is you can histogram the energy and direction of the detected particle. You can say, every time I had a count at so much energy, I produce a point in my histogram. And then you get a spectrum of the energies that were deposited. Or you could histogram the angle of that particle. You can then compare these spectra, these pictures, to models. People have to calculate what they expect is going to happen in order for you to see if you understand what did happen. So we always compare the data to models. And we try very often, always, to understand the shape of the spectra. Is it a flat spectra, for instance? Do you always have the same energies? Do you have just a random spectrum of energies produced in the detector? That would be interesting, but that would probably indicate that there's not much strange thing going on. Let me show you an example of some data and how we actually learned something about the physics, or what we decided that the data meant. Here is, the example is pion scattering on a proton. Now, I don't think I've mentioned pions yet. Maybe people know what pions are. Pion is a quark-antiquark pair. As I said, the quarks, you have 3 quarks inside of a nucleus. But you can also have antiquarks, you have antiparticles in general. And what happens if you take a quark and an antiquark and you pair them together, you can get a pion. So what people do is they produce pions, for instance, at an accelerator in Los Alamos. And then they can scatter those pions on a proton. And let's see what happens when you do that. Okay, pion scattering on a proton. What you have here on this axis is the energy of that pion as it was coming in before it was scattered on the proton. So here's the energy of the pion. On the top axis is basically the total energy of the proton that was sitting here plus the energy of this pion that was coming in. So the total energy of those 2 particles are here on this scale. And here's just the number of events that we saw. The number of times that this pion scattered on a proton. It doesn't, and we look at that as a function of this energy. So for instance, here what you see is that if the pion had 0 energy, you don't measure anything. You don't get any events. The number of events is 0. Gradually, as you increase the pion energy, you start to get more and more events. It turns out that you go through a big resonance here. You go through a big bump. You get to a maximum in the amount of events that you see, the amount of times the pion scatters, when you get to a pion energy of about 200 MeV. Now, 200 MeV in terms of CBAF energies is like a factor of 10 or 20 less than what we see used at CBAF. So these are experiments that were done with older accelerators, and now that we have CBAF, the idea is to look at even higher energies to see what happens. But with some of the accelerators that we've had for 10 or 20 years now, we've actually seen what happens. So here you see a maximum in the number of events, and then it tails off again. So when we see this kind of data, what do we think? Well, when you see that a lot of pions of a certain energy want to scatter from a proton, the way we interpret that now is that we've actually created a new particle. So we've had a pion and a proton coming together, and when you have just the right energy, you can create a new particle. You need just the right energy because that new particle has a certain mass. So you need just the right energy to create a new particle of a certain mass. So what we have here is what we call the delta resonance. We've created a new particle here, and that's the delta particle. Now, this is not the only set of data that led us to this conclusion. It's not that any time you see a bump in a spectrum, you say, oh, a new particle has been created. But this is one experiment out of millions of experiments that have been done where pions have been involved, or protons, or sometimes 2 protons coming together, and always at the same energy. In all these different experiments, we see a peak at 1230 MeV, basically. So we know that in all these different types of experiments, a particle has been created there. So all you have to do is look at the number of times you get a scattering and know your energy, and you can actually see this peak. So what I want you to take away from this is that if you can determine how much energy was deposited in a detector, and you histogram that, and you look at that data, and you look at it as a function of energy, for instance, you can actually look at the shape of a spectra, like here, and learn new interactions. You can learn that a new particle has been created, for instance. So let me show you a few pictures now of some of the detectors that we're actually working on. Some of the detectors that we're building here at CBAF in order to find even new particles. What we hope to do here at CBAF is to learn about yet undiscovered particles, for instance, yet undiscovered interactions between subatomic particles. And so we build very large detectors for that purpose. Here's one example. As you know here, there's 3 halls, A, B, and C. This class detector is in hall B. And I'm showing it to you because that's what I'm working on, so I like it best. What you have here is many different pieces of detector all put together to form one incredibly large detector. So you have a magnet at the center, produces a magnetic field, so the particles will curve in that magnetic field. And then around, for instance, inside these yellow pieces, in that hole there, you have some wire chambers, one kind of detector where you have wires and then the particles hit the wire. Then in between the magnetic coils, in between these yellow slices, you have another set of wire chambers that we call region 2, and that's what we're building at ODU, for instance. What happens is this whole thing is like an orange. It's like you have slices of an orange, and you're building it up larger and larger in layers. So you have some inside the yellow magnet, some between the coils of the yellow magnet, and then some outside of the yellow magnet, which is what you see here. And then we have even further out more layers of detectors. These are, for instance, scintillators, like the ones you see over here. And then in the front, in the forward cone, the beam comes in this way, into the middle, and you have a target here. And after the beam smashes into that target, particles are going to go out in all different directions. And what we want to do is we want to detect them in all of those different directions. We want to see all those particles if possible. That's why we're building a big detector that goes right around some small point, so we can see as many of the particles produced as possible. And as part of seeing those many particles, we have also detectors in the front. And you can see that this is a triangle. This is the calorimeter, and that's what you saw before, with the cosmic rays going through it, that's in the building on the other side of CBAF. This triangle here is what you saw with the computer demonstration. So this is a detector which is being built now. And I must say that building these detectors is actually really one of the most fun parts about being a physicist. It's one of the things that keeps me involved in physics. Learning physics is fun, and I like that also, but I am really one of those people that likes building these detectors. So that alone is fun and worth doing what we do. Here's a picture of one little piece of the small detector. It looks small in the picture, that goes in between the magnetic coils. This detector is, here are some people here. You can see that this detector is many times the size of a person. It's like the size of a small room. And what we have is 2 plates here, one here and one here. And we have to string 8,000 wires between these 2 plates. It takes months and months just to do one detector like this, and we actually have to build 6 of them, so we're in the process of doing this. But we have to put all these wires here, and then eventually these little pieces of the orange will be installed over in Hall B. So, since I have a minute, I want to show you a picture of some of the actual stringing that's going on. These are some people who are working at ODU. They're actually stringing some wires in between these 2 end plates. It's an incredibly difficult job because these wires are the size of a human hair. And you have to put 8,000 of them between the 2 plates, and all with the right tension so that they can hold high voltage, so that you can create a situation where a particle coming through will deposit energy. It's always a question of depositing energy in order to make a particle detector work. So these detectors, hundreds of people are working hard right now to build that big class detector. And in a year or so, we'll be able to see if it works. We're hoping. So let me just conclude by thanking some people who've helped me. One is Steve Gagnon, he's out in the back. Also, Brian Cross and Stan Majewski from the detector group here at CBAF have helped me very much to put these things together. And then we have Cole Smith, who's behind the computer from the University of Virginia. Thank you.
Thank you. Dr. Dodge has indicated she's willing actually to answer a few questions from the audience, if anyone is interested. Is somebody interested in having questions asked in this forum? Okay, then let's let people leave. And anyone who wants to ask questions or see some of the stuff up here, please feel free to come. Thanks a lot, Dr. Dodge. Great talk.
That's the most usual energy, yep.
Where's your treat? Can I borrow the notes tonight?
Is he sick or what?
Are you giving to you tomorrow morning?
I want one.
Patrick, he's kicking his ass. I hate him. Patrick, watch out! Don't hit your eye on that.
What's up, Ross? You on TV?